Now, let us do another one, x equal to y. We done this before, no, for multiprocessing. I did in last class. So, A is a matrix, x is a vector, and is y. So, what was the idea? If you recall, we had this matrix A, this vector x equal to vector y. So, this is m comma n, this is n comma 1, and this is m comma 1. So, I divide this among threads, divide array A. So, each thread will handle parts of the array A. Okay. So, we have 4 variables and my job is equally divided. So, my array multiplication is this start to end, but this start and end depends on the thread number. Okay. We did this in the past. So, just the division and multiply by vector, and the result, well, do the sum and is copied into product, which is y. So, it is summing over what these. Okay. And for every, this is also a range. So, this is doing twice, two things. For every row, it is doing the sum and copying on that row, particular row. So, this one line is very powerful. But Python is, that is the power of Python. It is very compact syntax. In fact, it is much easier to write, less error prone. We do not need to declare temporary variables. It is just one line. If you write in C, it will take something like 10 lines or more. And then I have the main. So, create threads in a loop, and the target is array mult. Right. So, this target will always be there. So, in your project, you need to divide the data and use the target for a expensive function. For finite difference, there is a loop. I mean, you need to work for all the rows and columns, right. So, you just need to divide the data and call this function for every thread. And once you initiate them, then you can join them, and after main runs, the whole, I mean, when main is complete, I will get a product which is y. Shared memory, so I do not need to do anything, I just need to print y or do something with y. Okay. So, these are the numbers done on Mac. So, unfortunately, Colab gives only 2 processors for free, and I did not find a really good speed up with the Colab. Maybe there are too many users on that memory, or so you need to, this threading and processing testing, real testing, for number testing, you need to use your own laptop. Turn off unnecessary process and run them. Okay. So, here so I am comparing multiprocessing with multithreading. So, we have this 3 configurations, 8000 by 8000, 8 million by 8 and 8 by 8 million. So, these are the numbers for process. One process I get this many seconds. For this data I get this data I get this. Okay. So, 8 by 8 million is good with one process. Threads number is, in fact, thread is doing better, 0.332 compared to 0.528 with one thread. So, threading, well, right now it is not parallel programming, this is sequential, but I am using the same code with single thread or single process. With the process, you need to use the earlier code, okay, the Wednesday class. If I use 2 process, then my number is from 528, it is coming down to 5319, and thread also there is an improvement, 0.226. With 4 threads, I get even further, in fact, very good improvement, 0.129, and with 4 processor it is 0.203. So, there is a, I mean, number is half, you can see, well, close to half, not half, maybe 80% improvement. So, for 8000 by 8000, there is a performance is not, I mean this should have been 1 if it is most optimal, but it is not. So, it is 0.64, whether it is the total time for that, I mean I have timed it in the loop, above the loop and below the loop. It is not for the full program, but it is the time for the loop. So, this is not bad. This is in fact is quite good, with 8 million by 8 is quite good, 0.81 is which is excellent, no? 0.81 is very good. So, this is the best configuration for threading, but for 8 by 8 million it is bad, 0.30. Okay, from 0.228 for one thread to 0.188 for 4 threads, the improvement is nominal, right. So, why is it bad? So, we discussed 8 by 8 million, it is because of false cache, false sharing, the cache issues, false sharing creates problem, and it is going to happen for multithreading too. So, when you write your code, I mean do not use configuration like this. Okay. So, when you divide your data, just be careful. Summary. So, multithreading and multiprocessing exhibit similar behavior. The table is, well, I mean multithreading is bit better, but table is showing similar behavior roughly, I mean efficiency wise. Multithreading is somewhat faster than multiprocessing, and they suffer from false sharing. So, we just have to be careful when you divide the data. Okay. So, there are other functions called OR lock, semaphore. I am not doing them right now. If time permits, we may do it later after our basic discussion on parallel programming is done. So, these are basically the wish list. So, I am not going to cover Fortran, but so connection to other libraries basically OpenMP, okay, that is what people use. OpenMP is same as multithreading. So, I will cover OpenMP with C++, okay, and we need to compare the numbers with C++, what do I get on the same core. There is something called pthread, which is more complicated. In fact, you do it yourself. OpenMP gives you a lot of functions. OpenMP is programming at the higher level, pthreads is programming at the lower level. Okay. You will get slightly better numbers with pthreads, but we have to do more work. Okay, homework, compare yourself multithreading and multiprocessing numbers. MP also I am going to start now after this, and we need to compare the numbers with Python, which is best within a laptop or on a node.